Hello. In this video, I'm going to be explaining problem 24 from the 2016 F equals MA contest. In this problem, we are told the moment of inertia of an equilateral triangle of mass m and side length a about an axis that passes through one of its sides. So it looks like this. And we're told the moment of inertia is 1/8 ma squared. And so now we are asked to find the moment of inertia of a regular hexagon of mass m and side length a about an axis through two opposite vertices. So the situation looks like this. So the key theorem that we need for this problem is called the parallel axis theorem. I will not attempt to prove it here. That deserves a video of its own. I will merely state the theorem and show how it is used in this problem. So basically, it states that if you have, some object and you want to find the moment of inertia through a point P and with a given axis, then what you can do is that, let's say there's the center of mass here, and you have an axis that is parallel to the one you want going through the center of mass, and that the distance between the point P and the center of mass is some length d. Then the moment of inertia about the point P is equal to the moment of inertia about the center of mass, or about that parallel axis that goes through the center of mass, plus m, where m is the total mass of the object, times d squared. And once again, d is the distance between the center of mass and the point, and your sort of different pivot point P. The unfortunate thing about this problem, well, fortunate or unfortunate depending on what you know, is that if you know this theorem, this is basically this problem is actually a pretty straightforward calculation exercise. But if you don't know this theorem, well then chances are you're not going to get this problem. You're not going to figure out this theorem in real time on the contest. So with that being said, let's look at our situation. We have a hexagon and sort of the obvious thing to do is to split the hexagon into 6 equilateral triangles. Now, each of these equilateral triangles has moment of inertia m over 6, so you have to be careful, right? But they do have the same side length a, as you can see. However, what about the axis? Well, if you look at these 4 triangles, which let me label with colored dots. If you look at these 4 triangles, 1, 2, 3, and 4, then these triangles are indeed rotating about one of their sides, either this side right here or this side right here. But if you look at these triangles, these 2 triangles, which I'll label with red dots, then they're not rotating about their side. Instead, they're rotating about an angle, they're rotating about a line that passes through the opposite vertex, and that passes through a vertex and is parallel to the opposite side. And so for those ones, that the same moment of inertia formula, the one that we were given 1/8 ma squared, will not be valid, and we will instead need to somehow adjust it to calculate the moment of inertia about this different axis, and we'll do that using the parallel axis theorem. So for, let's say, the blue triangles, and there are going to be 4 of these, the moment of inertia is 1/8 times m over 6 times a squared. And so that will be 1/48 ma squared. Now, what about the red triangles? Well, we will probably want, I think it would be good to start a new page for this one. if you look at this triangle, the center of mass, and this is a well-known geometry fact that you would just have to know, the center of mass is 1/3 of the height up. So if this is A, then you can calculate fairly easily that the height is the square root of 3/2 times A. And then you can see, because this would be a 30, 60, 90 triangle right here. So this would be 60 degrees. And so the height is root 3/2A, which means that this little height right here is 1/3 of that. So it's root 3/6 times A. And this height right here is root 3/3A, just the difference of these two, root 3/2A minus root 3/6A. Now, what is the moment of inertia? I'm going to draw these three axes, and I'm going to call them L1, L2, L3. Well, the moment of inertia about L1, that's the one we know. It's 1/8 ma squared. But it's equal to the moment of inertia about the center of mass, the parallel axis, L2, plus m. So in this case, we're assuming that the mass is m, and at the end, I'm going to divide by 6. So we're going to say times 2, divide by 6. It's always good to leave little reminders by yourself if you're going to make adjustments when doing your calculations. So plus m, so it's the moment of inertia about the center of mass, plus m times the distance. So, sorry, I realized that I labeled this incorrectly. So when I wrote the parallel axis theorem, I wrote this distance d, but what I meant to write is this distance between the two axes is d. So, sorry about that. Should have clarified that. So, all right. Sorry for that confusion. So we have m times the distance d squared. So what will that be? That will be root 3/6 times a squared. And so that will actually equal 1/12 ma squared. And so now, but what is IL3? It's going to be IL2, the moment of inertia about the center of mass, plus m times the new distance squared, so root 3/3a squared. And that's going to be 1/3 ma squared. Well, if you look at IL2, it's 1/8 ma squared minus 1/12 ma squared. And so this is actually going to be 1/24 ma squared. And if you put that into here now, we'll get IL3 is 1/24 ma squared plus 1/3 ma squared. So 1/24 plus 1/3 is 9/24, which is 3/8 ma squared. And so now, what is our total for the red triangles? It's going to be this quantity, 3/8 ma squared, but it's 1 times 1/6 because each red triangle only has mass m/6, and then times 2 because there are two red triangles. So 3 and 2 will cancel with the 6. We're going to get 1/8 ma squared. So we have 1/8 ma squared for the red. We have 1/48 ma squared for the blue, and so the total blue is 4 times that much, 1/12 ma squared. And so now, when we go back, so 1/8 ma squared plus 1/12 ma squared, that's going to give us a total so 1/12 plus 1/8 is 5/24, and so the total is 5/24 ma squared, meaning that our answer is option B. And that's all there is to this problem. Again, the unfortunate thing is that if you know the parallel axis theorem, and know the basic geometry facts about a triangle, which you could derive on the test, but it's better to just know them, then you can do this problem pretty quickly. Otherwise, you'll probably be taking a long time with this problem, or more likely, especially if you don't know the parallel axis theorem, probably not be able to solve it at all. So that is this problem, and I hope that was helpful. Thank you for watching.